If you think utility-scale batteries will scale faster because they're cheaper per kilowatt hour, you're thinking like an engineer, not like a system. Scaling energy infrastructure has almost nothing to do with cost curves, and almost everything to do with friction per deployment. This episode is not about which batteries are cheaper or which technologies are more elegant on paper. It's about why, in the real world, smaller, messier, distributed systems often outrun larger, more optimized ones. If you understand this distinction, a lot of recent energy outcomes suddenly make sense. In Series 1, we focused on valuation logic, how distributed energy assets create value, and why capital rewards speed and permission. This episode builds on that foundation. Here, the question is not what gets built, but how fast it can be repeated. This is where most models quietly break. Series 2 is about systems dynamics, why deployment speed beats unit economics, and why friction, not technology, determines infrastructure winners. By the end of this video, residential VPP dominance should feel obvious in hindsight, not controversial. Let's start with the intuition almost everyone has. Big batteries are cheaper per kilowatt hour. Economies of scale say utility-scale projects should dominate. That logic works beautifully in factories. Manufacturing rewards volume, standardization, and optimization. But infrastructure doesn't operate like manufacturing. Real-world deployment runs through approvals, politics, interconnection rules, capital timing, and human behavior. When you apply factory logic to infrastructure, you get forecasts that look clean and outcomes that consistently disappoint. Most people think scale means size. Bigger projects, lower per unit costs, more megawatts per installation. But in infrastructure, scale means repetition velocity. It's not about how big each project is. It's about how many deployments you can complete per year. Winners aren't determined by dollars per kilowatt hour. They're determined by months per approval, years per interconnection, and how many veto points can stop progress. That's the real scaling equation. Now let's compare friction directly. Utility-scale batteries must pass through interconnection queue reviews that often take years. They face environmental assessments, local permitting, political approvals, transmission upgrades, and long capital lockups before revenue begins. One project, one site, one delay can stall everything. Residential VPPs follow a very different path. A homeowner agreement, a service contract, an installation truck. That's it. 3 steps to deployment. Here's the simplest way to frame the difference. Utility-scale batteries scale serially. Each project moves through approvals in sequence. Dependencies stack. Delays cascade. A single regulatory holdup blocks the entire pipeline. Residential VPPs scale in parallel. 10,000 homes can say yes independently at the same time across jurisdictions. No single point of failure, no cascading delays. Pure parallel execution, which is exactly how fast systems scale. Arriving 1 year earlier doesn't just mean earlier revenue. Speed compounds in ways traditional financial models completely miss. Earlier arrival means earlier learning, understanding grid behavior, customers, and operations before competitors. It means earlier policy alignment, shaping rules while they're forming instead of adapting later. And it means earlier capital recycling. Revenue flows sooner, reinvestment begins sooner, and expansion accelerates while others are still waiting for permits. Infrastructure rewards whoever gets there first, not whoever looks cheapest on paper. Residential VPPs have an advantage most models ignore: optionality. Capacity can be added house by house, neighborhood by neighborhood, without massive upfront commitments. Deployment can shift geographically as incentives, grid needs, or regulations change. Operators can respond dynamically to policy shifts, utility programs, or emergencies. Utility-scale assets don't have this freedom. They're physically immobile, financially locked, politically exposed. Residential VPPs trade theoretical efficiency for flexibility, and flexibility wins in uncertain systems. When you look at real deployment timelines, the difference becomes unavoidable. Residential VPPs deploy in months. Commercial storage takes longer. Utility-scale batteries often take years. That 12-fold difference in speed creates compounding advantages that overwhelm any per-unit cost savings. By the time a single utility-scale project produces its first revenue, a VPP operator may have completed a dozen deployment cycles. At that point, the race is already over. Residential VPPs often look messy on spreadsheets, thousands of small assets, different homes, different regions, different owners. It appears inefficient. But that same distribution creates resilience. No single point of failure. Continuous learning across diverse conditions. Adaptive behavior under stress. Residential VPPs don't win because they're perfect, they win because they move. And systems that move adapt faster than systems that optimize in place. There is a specific penetration threshold where residential VPPs stop behaving like edge cases and start behaving like system infrastructure. Below that threshold, they're treated as pilots and niche programs. At the threshold, grid operators must account for VPP capacity and planning. Beyond it, VPPs become a foundational layer of the grid. Once crossed, grid economics, dispatch logic, and capacity planning fundamentally change. That transition is nonlinear and often invisible until it's already happened. Beyond that penetration point, the discussion stops being public. The specific threshold numbers, the grid stability implications, the regulatory arbitrage opportunities, those details matter more than any single technology bet. And they're exactly where serious strategy begins. That's also where this episode ends. Traditional analysis focuses on cost optimization, comparing dollars per kilowatt hour and finding the cheapest solution. Winning strategies focus on speed optimization, minimizing deployment friction and maximizing iteration velocity. Markets eventually figure this out, but by the time consensus forms, the window for asymmetric returns has already closed. The real question isn't whether this shift happens, it's whether you're positioned ahead of it or explaining it after the fact. If you're a founder, build for deployment speed, not just unit economics. Design around friction removal. If you're an investor, bet on velocity metrics. Watch installation rates, not just capacity numbers. If you're an operator, optimize for iteration speed. Each deployment teaches more than any model. If you're anywhere near energy infrastructure, this shift changes how you evaluate every opportunity, every competitor, and every strategic decision. TaBIS publishes analysis for founders, investors, and operators who need to think ahead of markets, not explain them after the fact. The next inflection points won't announce themselves. They'll be visible only to those watching the right signals, asking the right questions, and positioning themselves before consensus forms. If that's how you think, you'll find more work like this inside the TaBIS series. See you next time.